Picture this. You're strapped tightly into a passenger seat, looking out the window, and those massive engines start their deafening roar. In just a matter of seconds, hundreds of tons of metal, cargo, and people are going to literally defy gravity and hurl into the sky. It's an absolute marvel of modern science and engineering, right? Yet, most of us are just casually reading a magazine or taking a nap while it happens. Okay, let's dive into this explainer and uncover the sheer mechanical brilliance and fundamental physics that keep us safely up in the air.
Here is our flight itinerary for today's explainer. First, building the flying machine. Then, the physics of takeoff. Next, cruising altitude and engines, followed by landing and flight safety. And finally, we'll look at the future of aviation.
Section 1. Building the flying machine, anatomy and history.
Let's trace our rapid evolution for a second. For centuries, humans could only dream of flying like birds. Ancient civilizations invented winged myths, and later, in the 15th century, Leonardo da Vinci sketched his brilliant early flying models. But actual, practical, towered flight? That didn't happen until 1903 with Orville and Wilbur Wright at Kitty Hawk, North Carolina. It is just staggering to see how incredibly fast we've moved from that first wooden flyer to the massive, advanced passenger jets and spacecraft of the modern era.
Now, let's look at the absolute foundation of flight. Every single aircraft is locked in a constant battle of four fundamental forces. First up, we have the ultimate battle of physics, lift versus weight. Lift is our hero force here. It's the upward push generated primarily by the wings that directly opposes gravity. Weight, on the other hand, is the constant downward pull of the Earth. So the crucial point is that in order to fly, our machine's lift must completely conquer its massive weight.
The second half of this four-force equation is thrust versus drag. Thrust is the forward-pushing force produced by the airplane's engines. But as the plane pushes forward, the atmosphere pushes back. That air resistance is called drag, which includes both parasite drag from the plane's shape and induced drag from the wings. So thrust pushes us forward while drag fights back. Together, lift, weight, thrust, and drag dictate every single second of every single flight.
Section 2. The physics of takeoff. Forces at their limits.
Let's rapidly walk through the 5 precise steps of a takeoff. Step 1 is taxiing, just slowly moving into position. Step 2 is engine acceleration, where pilots throttle up for maximum thrust. Step 3 is forward motion, accelerating rapidly along the runway to build up airspeed. Step 4 is rotation, hitting that specific speed where the pilot finally pulls the nose upward. And finally, Step 5, liftoff. At this exact moment, the upward force of lift finally becomes greater than the downward force of weight, and flight is achieved. But how do those wings actually generate that winning lift? The answer is the airfoil. Now, what's really interesting about this slide is how this specific shape is the absolute secret to making heavy metal fly. Notice the design. It has a curved upper surface and a flatter lower surface. This streamlined profile is purposefully engineered to slice right through the air, reducing drag while vastly increasing both lift and fuel efficiency.
To understand why that curved shape matters so much, we turn to the Bernoulli principle. It states that when the speed of a fluid increases, its pressure decreases. I want you to imagine the air behaving exactly like a rushing fluid river. As the airplane moves forward, the air traveling over that curved top surface has to move faster than the air moving under the flatter bottom surface. Faster air on top creates lower pressure. Slower air on the bottom creates higher pressure. That high pressure literally pushes, or sucks, the plane up into the sky without getting bogged down by a bunch of complex equations.
But Bernoulli doesn't work alone. Physics fans, meet Newton's third law. For every action, there is an equal and opposite reaction. Newton pairs perfectly with Bernoulli here. As the airplane hurtles forward, the physical angle of the wings pushes the rushing air downward. And because the wings push the air downward, the air pushes the massive airplane upward. These two laws of physics work in perfect harmony.
This brings us to a really critical term, the angle of attack. This is the specific angle between the airplane's wing and the incoming airflow. When the pilot rotates the plane's nose during takeoff, they are increasing that angle of attack. Pitching the wing up increases the lift, which is absolutely necessary to leave the runway. However, it's a delicate balance, because pitching up too steeply leads directly into our next concept.
So what happens when a plane stalls? A stall is not the engines shutting off. Rather, it's a sudden, dangerous loss of lift. This happens when the angle of attack becomes excessive, or the airspeed drops too low, and that smooth airflow over the top of the wing gets completely disrupted. Without that smooth airflow, you lose your pressure difference, you lose your lift, and the aircraft can descend rapidly. It sounds terrifying, but reassure yourself with this. Modern pilots train extensively for this exact scenario and know exactly how to recover safely.
Section 3. Cruising altitude and engines. The cruise phase. 35,000 feet. That's over 6.5 miles straight up. Commercial jets cruise safely above this altitude for a very specific reason. Up here, the air density is much lower. Thinner air means way less drag against the fuselage, which allows the airplane to fly faster and burn significantly less fuel. It's the absolute sweet spot.
Of course, to fly high and fast, you need serious power. And this brilliantly illustrates how modern jet engines transform compressed air and fuel into massive thrust. Step 1. Massive amounts of air enter the front. Step 2. Spinning compressors forcefully squeeze and pressurize that air. Step 3. Aviation fuel mixes with this super compressed air and ignites. Step 4. Those incredibly hot, expanding gases rush out the back. And Step 5. Thanks again to Newton's third law, that backward rushing exhaust creates the reaction force, thrust, that pushes the airplane forward at hundreds of miles per hour.
While cruising at these speeds, safety is paramount. Flying is considered one of the safest forms of transportation in the world. We have advanced radar and autopilot for pinpoint precision. We have highly sensitive weather detection to route us around thunderstorms and ice. We have the famous black box, which is actually bright orange, recording all flight data. And regarding weather, while things like jet streams or mountain winds can cause turbulence, it is mostly just uncomfortable. It's rarely dangerous to the aircraft.
Section 4. Landing and flight safety, returning to Earth.
Landing is a highly calculated 5-step process. First is the descent, gradually losing altitude. Second is the approach, aligning perfectly with the runway. Third is flap extension. Flaps are movable surfaces on the wings. By extending them, the pilot increases the wing's surface area, which maintains lift even as the plane drastically reduces its speed. Fourth is touchdown. And fifth is braking.
Braking a heavy jet going over 100 miles an hour isn't like stopping a car. There are 3 incredible mechanical features that violently but safely halt tons of forward momentum on the runway. First, heavy-duty wheel brakes. Second, reverse thrust, where the engine exhaust is physically redirected forward to push against the plane's momentum. And third, spoilers. These are panels that pop up on top of the wings to instantly kill the remaining lift and drastically increase drag, planting the plane firmly onto the runway.
Section 5. The future of aviation. Cleaner and faster.
Let's move to the future and see how this builds into something even more exciting. To solve the environmental impacts of modern flight, scientists are rapidly developing sustainable aviation fuels, hydrogen-powered planes, and fully electric aircraft for zero-emission flights. But it doesn't stop there. We are looking at a return to supersonic passenger jets that cross oceans in a fraction of the time, and even autonomous, pilotless flying taxis that could revolutionize everyday urban transport. Before we wrap up, let's do a rapid-fire recap of our key aerodynamic terms. Lift is our upward force. Drag is our air resistance fighting back. Thrust is our forward push. Gravity is the downward pull. The airfoil is that magical curved wing shape. Flaps are the movable surfaces for slow-speed lift. A stall is that sudden, dangerous loss of lift. And the runway is the very path where this entire cycle of physics begins and ends.
From the ancient wing myths to the Wright brothers, all the way to massive jet engines cruising at 35,000 feet, the evolution of flight is a testament to human innovation. We conquered the 4 forces of flight, and now we are redesigning them for a cleaner future. Which leaves us with one final thought based on the incredible tech currently in development. Will your next daily commute be in a zero-emission flying taxi? Keep looking up at the sky because the future of aviation is arriving way faster than you think.